Thank you very much. I'd like to acknowledge the traditional owners of the land where we meet today and of the place where I work in Townsville, the Bindle and Bulgur Kaba. So we've just been talking a lot about metapopulation, and it's mentioned that, yes, they're all using dispersal in the background. And so that's what I'm actually going to talk to you about now. So as part of the decision making, and it was done during the 2004 rezoning of the GBR, it was actually talked about that biophysical modeling and better understanding dispersal was really important to, well, that's what they're explaining with where are the corridors, where is the migration, and how we should actually support that. However, in 2004, we didn't have the capability or the modeling that we have now. So this was kind of the idea, and now actually dispersal is being used to make decision, and that's a bit difficult to talk about it with Sam in the room, but so for COTS, please feel free to correct me if I make any mistakes, but for COTS control prioritization, actually now dispersal is 2 of the 5 key input that comes into the decision. Thank you very much. And that comes to a value that is the ecological value, and there also a tourism value. If you've got any question, you'll have to talk to Sam exactly about how it comes up with using all of these inputs and just making. But this is used to actually make a list. So every year they go through the process, and they make a list based on what are the reefs that they should prioritize based on where the COTS are, what reefs are going to be affected by them due to dispersal. So that is something for Sam. But I wanted to just step back a little bit and say what is actually needed to understand dispersal. And this is pretty much a 3-step work. The first step is to understand what is happening on the reef. What are the ocean currents doing? So that's your first step. You need a hydrodynamic model that is actually going to show you what's happening around the reef. The Great Barrier Reef is extremely complex. So you're going to have some trouble depending on what you are actually going to resolve. What are the processes that you're going to resolve depending on the type of model that you're going to use. And so these flow fields that you get from this model are being used to actually drive your trackers, your particle trackers. That's where you set all of your, when is the spawning happening? So you start driving, so you go from a Eulerian world to a Lagrangian world, where you're actually moving your particles with the currents. And then the third step, and it's where you have even more variability, is what do you know about the biology of these little larvae? Do you really know when they are going to be spawned? Do you really know where they travel in the water column? Do you really know when they're going to be competent to actually settle on the reef? And so that's your last, when you're actually getting your connectivity matrix. And this is actually the input that is being used for the reef prioritization, but also inside a lot of the metapopulation model. So in our project, what we thought was, okay, we probably need to do a bit of a review. What do this model actually represent? And so our aims was to evaluate the model prediction. What is the uncertainty that is coming from the hydrodynamic? What is coming from the uncertainty of the biology? So one way of dealing with it is doing some sensitivity analysis. And how do you transform this information to be the best key input for management? So the method that we use is we kind of got a bunch of people together, so key expert in their field, and so in hydrodynamic modeling and trackers, but we also got a lot of the ecology and biology, because we needed to also update, so integrate the knowledge that has been done in the last few years and put that inside. Also look at how other ecosystem drivers such as temperature and salinity could actually affect what's happening in our system. And so for this, we also got the management on board, which is, so, they should have their word to say. And so the idea was to say, are the models that we're using representing what they need, which is reef scale intervention. And so what we did is, we went a bit overboard, I have to admit. We went with 3 different hydrodynamical models. These 3 models have been validated, have been for the Great Barrier Reef. They've been used, they've been published. And what actually varies with them is there's a lot about the resolution, but there's also about the way that they're representing. So some are depth average, some are 3-dimensional, some just do the barotropic, some also include the baroclinicity. So these 3 models were then, so one is actually run by ERIF, but they were run for the periods where we needed to understand COTS dispersal. And we varied the frequency of release to capture as much of the variability that you have during the summer season, which is due to the monsoon trough just wandering around and being also driven by climate drivers such as ENSO. And we also varied the egg buoyancy, so we actually the biologists told us, well, you should actually test this. So we've run a range of tests. And then we've also updated the post-processing, same with the biologist. And so all of this ended up being that result. I know I shouldn't have presented it, thank you very much. But that's pretty much kind of I know. So 5 minutes, thank you. So yeah, that is kind of a summary pictures of what we've produced over all of these. And the idea is they are kind of similar. That's the connectivity matrix. So source to sink. I added the latitude on it because I like it. And it was just to show you that there's variability, but there's a lot of agreement between the model as well. And so the first one is slim, so it goes down to 250 around the reef. The second one and third one are actually the same model, but we've used different tests, so moving the particles so they could actually go at different depths depending on their age. And the third one is run by ERIF as well, so it's using GBR-1. And so the idea was, actually, do we see any agreement at reef scale? And I think this picture is actually representing what is going inside the reef prioritization. So they're using network properties, these 3, for example, so out component, total node strength, and the node out degree. And so each of the colors represent the model comparison 1-to-1. And what you can see is there's not that much agreement at reef scale. However, if we step back and we look at this matrix and we say, okay, so maybe we don't have that much agreement at reef scale, but if we start looking at what reefs are actually really connected to each other, can we actually find a different way of looking at the reef that could be maybe more beneficial for management? And that's what we found. Like if you actually, it's a simple cluster algorithm, but it looks at the connections between the reef. And what we found is actually the 3 models at the surface tend to agree pretty well. So they find the boundaries are quite similar from one model to the other. So that could be a different way of adapting management to dispersal model output. And however, what we found also is it's very sensitive to the biology. Therefore, you just change a little bit, which was instead of having the dispersal being kept at the surface, we actually let them go deeper, which was what the biologists told us could happen. And then you end up with different communities. And so I think it kind of shows that biology is extremely important to dispersal. So what we've learned is we're probably not resolving with this regional scale model, the reef scale. But we may actually be onto something into understanding better how groups of reef are actually connected. The gaps in the COTS larval biology is something, and I think we're mentioning COTS here, but I think it is true to anything that lives and uses pelagic larval life at one point of their life on the GBR, means that yes, there's still a lot of work to be done. And so moving forward in a very highly variable environment, we should probably go towards a higher resolution in hydrodynamic. So I think that's one point that is going to be mentioned again in the next two talks, that this is needed. Larval biology is also something that we're going to have to spend more time and money on. And we actually, all of these results are already used as input into the reef prioritization. Well, thank you very much. That's everybody that has had an input in this project. It has been great to work with all of you. And that's it. I've just left that as this is the output for the project.
Thank you, Severine. We have just 2 minutes for questions, so I might take one quick question from the audience. If a quick question is possible, Chris.
Thanks. The clustering, is it based on sink or based on source? I just wonder if, like, how did you cluster? And is there, like, genetic study that would confirm what you found in terms of, like, clustering?
It is based on the dispersal strength between reefs. So it's not just source and sink, it's how well connected you are to your neighbors. The genetic, I think, well, talking to the LTMP, they love that community, not for the COTS, but it kind of talks to them because it's like, well, actually, we can relate some of the community that you've been observing to this. It'd be better to do it for fish, and we've got the data, so we should run it. But yeah, genetic is something that is hard to come across in the GBR, but we've had the chance, and there's few of us here that have actually used parentage analysis in other places. And yes, it would be great to have more validation. It would be, yeah. We're up, like, if you get genetic data, we would love that. Thank you.